It's time to start the session again. It's 11:15, not 10:15 in China time. The first speaker of this second session is Dr. Bowen from Colorado Mountain College. She will talk about the electromagnetic considerations of the nuclear force, part 2. So please start talk, please.
Okay, thank you. Welcome to my talk, the Electromagnetic Considerations of the Nuclear Force, Part 2, the determination of the lowest energy configurations for nuclei. I presented Part 1 at the last ICCF conference, and I would like to briefly review the electromagnetic model. The electromagnetic model is similar to the residual chromodynamic model in that there is an internucleon quark-to-quark bond connecting the nucleons. However, for the electromagnetic model, this bond is not related to chromodynamic color, but rather it is electromagnetic. The bond exists between the positive and negative charges of the quarks, as you can see in this figure. The up quark is a plus 2/3 in elementary charge, represented by the plus sign, and the down quark is a negative 1/3 in elementary charge, represented by the minus sign. A pair of quarks is needed for one bond, as shown in the figure. Each nucleon can bond a maximum of 3 times. Here are the equations I use for determining the electromagnetic energy of the nuclide's configuration. For electric energy, I do a double summation of every charge to every other charge. For magnetic energy, I do a double summation of every magnetic moment to every other magnetic moment. Notice that for the magnetic energy, vector math must be used, as it is a more complicated vector equation. I use computer programs that I have written to run this calculation. I point this out to impress upon you that the results I get are not simply estimates or rough calculations. They are the actual detailed calculated energies for a configuration of charges and magnets. There are some quantum considerations I take into account, specifically the kinetic energy of the quantum angular momentum for each nuclide. I do not use the simple equation for a spherical object. Rather, I do the calculation for a non-spherical object considering every nucleon in the configuration. This is a more involved computation, again, requiring a computer program to calculate this. Another consideration is that static electric dipole moments are not allowed by quantum physics. The implication is if there is a static electric dipole moment in the configuration, then there must also be a quantum spin. A third quantum consideration is the Pauli exclusion principle and the hardcore repulsion associated with that. Nucleons cannot overlap in their spatial dimensions. Thus, doubly bonded nucleons and triply bonded quarks are not allowed. Let me discuss how I determine the lowest energy configuration for each nuclide. Each quark goes into a matrix with its XYZ coordinates, its charge, its 3-dimensional vector magnetic moment. The total energy of the configuration is determined using the electromagnetic and spin equations and computer calculations. The various possible configurations are compared, and the lowest energy configuration is then determined. These configurations that I present are not mere speculation. For example, I have over 20 files just for beryllium-9 in order to determine its lowest energy. I want to discuss the similarities of the electromagnetic model with the cluster model. The cluster model claims that nucleons cluster into segments. A segment is a group of one or more nucleons, and it is the alpha segment that predominates. These segments form a chain-like structure, as you can see in these figures here on the right. This clustering phenomenon is experimentally verified, and the cluster model has gained a lot of attention as a result. The electromagnetic model also claims that nucleons cluster into segments. There are a few differences, however. This model takes into consideration electric dipole moments. Also, this model considers exactly how the segments bind to each other. And there are more types of segments. The main difference, however, is that the electromagnetic model explains why. Why do the nucleons cluster, and why is the alpha segment the predominant one? Because clustering is caused by the electromagnetic force putting the nuclide in its lowest energy configuration. Recall that each nucleon can bond a maximum of 3 times. This fact causes nucleons to cluster into alpha segments. As you can see in these figures, if there were only 2 bonds per nucleon, they would just link together like a string of beads. In this top figure, you can see that each nucleon has 2 bonds. In the next figure, there are 3 bonds per nucleon. And because of that, they form alpha segments like this. As you can see in the second figure, there are 4 alpha segments linked together in a chain. And each nucleon has 3 bonds. The lowest energy configuration is with the most number of quark-to-quark bonds, with the net positive charge spread out as far as possible, while still maintaining the bonds. And any negative charge in the configuration will be situated within the highest concentration of positive charge. Combining the segments in the lowest energy state, they form a chain, as seen here. This chain may curve or form a helix. However, there is no branching of the chain. It is not like that lower figure. Now, I want to introduce to you some simplified graphic representations for the proton and neutron. In this first figure here on the left, you can see the spherical nucleons with the 3 quarks in each one. Red is the up quark with a plus charge, and blue is the down quark with a minus charge. In the second representation, it is even more simplified without having to show the round sphere, but just the triangle of the quarks. The third representation is simpler still, showing either a red or blue triangle for a proton and neutron. So given these simplified representations, here are the configurations of deuteron, triton, and helium-3. You can see the bond between the plus quarks and the minus quarks. To the right are the symbols for the segments, showing the triton segment as a large triangle with a T in it, and here is the helium-3 segment as well. The next nuclide is helium-4. Now the configuration for helium-4 is unique. It is the only nuclide with all of its quarks bonded. The thermal neutron cross-section for helium-4 is absolutely 0, not just extremely small, It is 0. And you can see why very easily. There is no place in this configuration for a neutron to bond. Helium-4 has 6 bonds, as you can see in the figures. 1, 2, 3, 4, 5, 6. Compare that to triton or helium-3, both of which have 3 bonds. This explains the large jump in binding energy. Also, helium-4, the separation energies are the highest for any stable nuclide. And that is because to remove a nucleon, 3 bonds must be broken. Now, helium-4 is not a segment in any nuclide. Rather, the alpha segment is what predominates. And here is the configuration for the alpha segment. As you can see, the alpha segment has 1 less bond than helium-4, and that allows it to bond to the other segments. There is a plus-plus quark on one side and a minus quark on the other, connecting it to the rest of the nuclide. That last figure in the lower right shows the representation of the alpha segment. There is one more important segment I would like to discuss, and that is the star segment. You can see its configuration here. This segment puts a negative charge in the center of the configuration for lower energy. The 2 plus-plus quarks, here and here, will bond to the rest of the nuclide, while the 2 minus quarks remain unbonded. They offset and separate the positive charge of the nuclide. Most importantly, this segment removes the electric dipole. All right, reviewing so far, here are the various segments used in the electromagnetic model. The alpha segment is predominant. The excess neutrons or protons will form single nucleon segments shown here. A triton segment is included in all stable odd Z nuclides. An He3 segment is similar to a triton, but it has an unbonded plus-plus quark rather than an unbonded minus quark. As I just described, the star segment is included in most stable nuclides near the center. Now, I have only labeled the unbonded quarks, but please keep in mind, there is a positive charge throughout all of these segments. The next stable nuclides are lithium-6 and lithium-7, shown here. Note that there are other possible configurations, but they are either not the lowest energy or they are not stable because the electromagnetic forces would cause them to attempt to double or triple bond. Here are the diagrams of the lowest energy states for beryllium-9 and boron-10, as you can see in these figures. Now, I want you to do a little thought experiment. What would happen if a slow-moving neutron with its 2 unbonded negative quarks got close to boron-10? The 2 minus quarks would bond to the 2 plus-plus quarks, and an alpha segment would form. By the way, the thermal neutron cross-section for boron-10 is 3,840 barns. That is huge. Here are the diagrams for boron-11 and carbon-12. From carbon-12 up, there is a pattern for stable nuclides. Let's take a look at that pattern by examining the next several nuclides. Here are the diagrams of C13 and through N15. The extra neutrons go between the alpha segments. Here are the diagrams of oxygen-16 to fluorine-19. The pattern continues. Here are some examples of more nuclides. Let's skip to calcium-40. This is the largest stable nuclide made up of only alphas. After that, more neutrons are needed to offset the positive electric field. If we don't add more neutrons with their unbonded minus quarks, the electric field in the vicinity of the nuclide becomes too high. And when this happens, an instability like electron capture or beta plus decay is more likely to occur. To summarize this basic pattern, these configurations are based on the lowest electromagnetic energy. They are not just mere speculation. There is one alpha segment for every 2 protons and 2 neutrons, and there is one star segment near the middle. If n is greater than z and z is odd, there will be one triton segment in the nuclide. Extra neutrons are interspersed between the alphas, and the segments bond together to form a chain-like structure. Now let's look at this basic pattern for larger stable nuclides. If there are enough extra neutrons, they form what I call an H4 segment. This is similar to an alpha, but it has 3 neutrons and only 1 proton, as seen here. This means it has 2 down quarks on the ends, and there are no unbonded plus-plus quarks in the configuration. For example, look at iron 56, shown here. You can see how tightly bonded it is, and there are no unbonded plus-plus quarks to give it a high electric field. Now you can understand why it has the strongest binding energy per nucleon of all stable nuclides. As the nuclides get larger and larger, more unbonded quarks are needed to offset and spread out the positive charge. These neutrons go in between the alpha segments, and this pattern continues all the way up to bismuth 209. Above bismuth 209, there are more extra neutrons than alphas. Then the neutrons double up in pairs with no alpha in between. There are no stable nuclides with doubled up neutron segments. I find that very interesting. Now let's look at the radioactive with Z greater than N. For these nuclides, there are either single proton segments or He3 segments, both of which have the unbonded up-up quarks. For example, carbon 11. Here is the electric field near the nuclide.
Please make a conclusion.
In conclusion, structure is what dictates the nuclear behavior of the nuclide. The electromagnetic model is able to achieve excellent predictions of binding energy, as was discussed in part 1. There are other numerous nuclear behaviors that this model can explain. For example, excited energy states. These are simply different configurations, perhaps with different spins, but always with different configurations. Particle decay, that is when the electromagnetic forces within the nuclide attempt to double or triple bond. Large quadrupole moments, that is due to the chain-like structure of the lowest energy state. We can explain some of the large thermal neutron cross-sections. It occurs when there is an He3 segment on the end. Also, instability is more likely to occur when there is a high positive electric field in the chain-like structure. Additionally, the separation energies depend strongly on how many bonds must be broken to remove a nuclide. Thus, we can now understand that nuclear behaviors are a direct consequence of structure. By recognizing the electromagnetic forces that within a nuclear structure, we can better understand nuclear behavior. Thank you for your attention, and I will take any questions.
Okay, thank you. But unfortunately, your time is up already. So if you have just one question, I take it.
Okay.
Egorov, go ahead. Egorov. No? So I don't think.
Okay. I cannot to switch on a microphone. Excuse me. Lynn, I suggest with you that structure is a key of understanding nuclear reaction, but I can suppose that in the quark model work not an electrical fields, but
Which model are you talking about? Which model?
not work an electrical field. Electrical fields, electrical force.
Okay, yeah.
There are not electrical force and electrical fields, but they work in magnetic fields and magnetic force. But in this force, the magnetic field is in specific form, in specific backup. No, but it is magnetic field connection on themselves. Like, oh, excuse me, a second. Are you look me?
Yes.
Oh, what?
Okay. The magnetic.
In this and in this case, distances will be more or less, and forces larger.
Yes.
Thank you very much.
And the magnetic field, the magnetic force is actually somewhat stronger than the electric force when you put the two quarks together and they bond both electrically and magnetically. So yeah, the magnetic force is very important. Also, the dipole moment of the magnetic force, whether it aligns in a strong bond or misaligns in a repulsive bond, or is maybe some kind of in between, that makes a difference in how strongly bonded that quark-to-quark bond is going to be. I hope
Okay.
that answers your question.
Okay. Okay. Please.